Добрый день. Это запись лекции, которая была в пятницу 9 октября, но запись сделана во вторник 13 октября, потому что на той записи не получился звук. А, Теперь я перехожу на английский. Okay, let's switch to English. So let's recall briefly what was in the last class. First of all, we had the following two bounds called Gilbert bound and uh, volume bound or Hamming bound. The Gilbert bound provides a necessary condition for existence of an NKD code over Q letter alphabet. So what mean these parameters? N is the block length, that is the length of the code words. K is the log base Q of the number of messages, code words, that is K is the length of the messages, and D is the minimal distance, Hamming distance between different code words. So both bounds say something about whether such a code exists or not. Sufficient conditions look like that. If the volume of the Hamming ball of the radius d minus 1 times q to the k is less than q to the n, then the code exists. And this is called Gilbert bound. And the sufficient condition, the necessary condition, looks in a similar way, but instead of d minus 1, we have d minus 1 over 2. This is volume bound. Usually one takes the log base q and then divides by n, and so both bounds look in the logarithmic scale like that. Log q of the value of the radius d minus 1 ball over n plus k over n is at most 1, and here we have the same expression, but the radius is twice less. The reason why we like this form of both bounds more than the original form is that k over n has the ratio k over n has a clear meaning. It's called the rate of the code. And so both bounds say establish some upper bound for the rate, which is possible for the given distance. But to understand what those bounds really mean, we need to estimate the first terms in both bounds, and to this end we have seen that the following lemma holds. So we do not have to compute this logarithm exactly because it's divided by n, and so to estimate with precision, say order log n, would be enough for our goals. And the lemma states that this log, the logarithm of the volume of the Hamming ball of some radius r, is as much as possible it's n plus order log n if r is more than 1/2 of n. And otherwise it is equal to the Shannon function n times the Shannon function of r over n plus order log n. If r over n is less than 1/2. And the formula for the Shannon function h2 is as follows: h2 of x is equal to minus x log x, all the logs now are base 2, minus 1 minus x log 1 minus x. So when we will apply this lemma, of course we can ignore d minus 1 in both bounds, because if r is changed by 1, the ratio r over n is changed by at most 1 over n, so this change is negligible. So actually it's not hard to see that when the radius is increased by 1, the volume of the ball is increased at most n plus 1 times. So when we take the logarithm, this difference becomes log n, and so it's not important here whether take r or r minus 1, the formulas are the same. So let's, to understand what areas indicate these two bounds, let's see how the graph of the Shannon function looks like. To this end, we will use Wolfram alpha. So here I asked Wolfram alpha to plot the Shannon function, and you see its graph is symmetric. It has the x-axis of symmetry, this one, and the maximal value is 1. So it is attained where x is 1/2. So that means that if for the Shannon function, for the first bound, that means that if d, well, let's rewrite both bounds, using the Shannon function. So the first one looks like that: h of d over n, the Shannon function, plus k over n, so is at most 1, and the precision here is of order log n over n, because we divide by n, and this looks like the Shannon function of d minus d over n, so we can ignore minus 1, plus k over n is at most 1. Or we can say that this establishes the following upper bound for the rate. The rate is at most 1 minus the Shannon function of the relative distance, and here, and this is, sorry, d over 2, and this is the necessary condition, so the rate can't be larger, and this is the sufficient condition. If the rate is less than 1 minus the Shannon function of d over n, then such such a code exists. And so let's go back. For example, let's see what area indicates this one. The necessary condition k over n is at most 1 minus h of d over n. So we will ignore this small term. So we see that we obtain the following. The following. So we need to plot now 1 minus the Shannon function, and the largest value is 1, so we do not need to consider x's which are larger than 1/2, because when the radius is, when d over n is 1/2, then the rate already becomes 0, and we obtain the following graph. So this is the graph of the Gilbert curve. So it indicates this area below this blue line, and in this area for all the parameters. So in this area the code exists. This axis is d over n, so we see that if d over n is something like 1/2, 1/5, then the maximal rate is something like 0.23, and if the relative distance is 0.1, then the rate becomes like that. It is about 1/2. So this was the necessary condition, and to plot the sufficient condition, and to plot the second area in which represents the volume bound, we need divide here everything by 2, all the x's by 2, and we then obtain the graph of the volume bound, which is obtained from this graph just by stretching in the horizontal direction, where the stretch factor is 2. So, and again, this area indicates the area where is no code. For example, from this picture, we see that if the relative distance is, say, 1/2, there is no code whose rate is larger than 0.2. And between two bounds, there is a large area where nobody knows. It's unknown, at least we do not know whether the code exists or not. Let's go back to the Jamboard and see, and let's plot here our curves. So this is the first axis where we have k over n, the rate of the code. Here we have the second axis where we have d over n, and so the first bound, assume that this is 1, the first bound is the volume bound. It looks like that. So no code here, and the second one is obtained from this one by shrinking, where the shrinking ratio is 1/2, and this is the yes area where there is a code, and this is the question mark area where we don't know whether the code exists or not. Later we will reduce this unknown area, but up to now we need to understand how both bounds look for arbitrary alphabet. Recall that all the bounds we have plotted so far are in the case Q of the binary alphabet. So let's go back to the arbitrary case, and in the arbitrary case we need to understand, we need to prove an analog of this lemma, which estimates the log of the volume with logarithmic precision. So the generalization of this lemma is the following one. For arbitrary Q, we have the following bounds. So the logarithm of the ball of radius r is equal to n plus order log n if r over n is larger than q minus 1 over q. So note that q minus 1 over q in the case of binary alphabet is 1/2. So we obtain the same threshold here as we had before. And otherwise, it is obtained by the generalization of Shannon function, n times the Shannon function of r over n plus order log n in the case when r over n is less than this threshold. So let's prove this lemma. Obviously, we can calculate the volume of the ball using the sum of binomial coefficients. So the ball consists of all strings at the Hamming distance at both r from some fixed string, the center of the ball, and we have one string at distance 0. How many strings are there at distance 1? We have n ways to choose the symbol which we change, and q minus 1 ways to change it. Because previously, in the case of the binary alphabet, we didn't have this factor because q minus 1 was equal to 1. But now it matters. Plus n choose 2, the number of ways to choose two symbols, times times q minus 1 to the squared, and so on. The last term in this sum is equal to n choose r, the number of ways to choose r symbols to change, and q minus 1 to the r, the number of ways to change those r symbols. First of all, let's understand then that for r equal to n, we obtain the sum of all binomial coefficients, 1 plus n choose 1 times q minus 1 plus n choose I, q minus 1 to the I, plus, and the last one will be n choose n times q minus 1 to the n, which is obviously equal to q to the n, because the ball of radius n contains all the strings, and there are q to the n of them, because we consider n letter strings over q letter alphabet. So for arbitrary n, we have just some part of this sum. For arbitrary n, we choose some r terms, or actually r plus 1 terms from this sum. Because the number of terms in all such sums is at most n plus 1, up to a factor of n plus 1, that any of this sum equals its largest term. So we need to understand what is the largest term in each of these sum, and then we will replace the sum with its largest term. So we need to understand how these terms change as I increases. And it turns out that they first increase up to the place where, say, call it A0, I0, which is approximately equal to n times q minus 1 over q, and then they decrease. And to find this place where they increase, where we have the maximal term, we just need to calculate the ratio between I plus first term and i's term. So in other way, in other terms, we need to understand what is the ratio between n choose I plus 1 q minus 1 to the I plus 1 and n choose I. So recalling the formula for the binomial coefficient, we see that this is equal to n factorial over I plus 1 factorial, n minus I plus 1 factorial And here we have again n factorial, I factorial, n minus I factorial. So, and q minus 1 to the I cancels, and we obtain q minus 1 in the numerator. So now we see that n factorial cancels, I factorial, and so on, and we obtain the simple expression n minus I over I plus 1 times q minus 1. So now we need to understand where, for which I, this becomes less than 1. First of all, because this I is that I for which the term is maximal. And it is easy to see that if I increases, then n minus I decreases, and 1 over I plus 1 also decreases. So we see that indeed when I increases, this ratio decreases. So, and so at some point it becomes less than 1, and this is the point where the terms, the increase is changed by the decrease. So you need to find for each I this is 1, and another way we need to solve the equation I plus 1 over n minus I is equal to 1 over q minus 1. And we do not need to solve this equation exactly, because if we our precision will be say plus minus 1, it's enough for our goals, and so we can actually ignore this plus 1, and instead of this equation solve equation n minus I over I equals q minus 1. Oh, sorry, here I confuse the numerator and denominator. So n minus I over I equals 1 over q minus 1. And the solution to this is n over I is equal to 1 over q minus 1 minus 1 plus 1, sorry, which is q over q minus 1. So you see that the largest term, we have the largest term when n over I is q minus 1 over q, or in other words, I over n is equal to q minus 1 over q. Sorry, we have q here. Now let's go back to the statement of our lemma. So the largest term has this index. When r is larger than this I0, then the sum obtain the sum of those terms has their absolute largest term, and that means the sum is already becomes close to q to the n, because the largest term in the whole sum obviously is at least q over q to the n over n plus 1. And so if r over n is larger than q minus 1 over q, which is our I0 over n, then the log, the volume is already at least q to the n over n plus 1, so up to order log n, it is 1, n. Otherwise, when r is less than that I0, we have the sum of some terms who increase. So the sum up to a factor of n plus 1, or to be more precise, up to a factor of r plus 1, is equal to its largest term. So we have, in that case, we have that the size of the ball is equal to the last term, to this one. And we need just to express this logarithm of this term as a Shannon, using the Shannon function. Let's do it. It's a simple exercise. So what is n choose r? Q to the q minus 1 to the r. It is n factorial over r factorial n minus r factorial times q to the q minus 1 to the r. So in the last class, we have seen that up to a polynomial factors, the binomial coefficient equals to n over r to the r times n minus r n over n minus r to the n minus r. So we obtain the following. And when we take the log, so this is the size of the ball up to a polynomial factor, and if we take the log of this, log base q of this, we obtain r times the log n over r plus n minus r log n over n minus r plus r times log q minus 1 base q. Now this this is usually expressed using the Shannon function. So this is usually expressed as the Shannon function n times the Shannon function, n times the Shannon function of n over r over n. And the formula for Shannon function is just made this to be true. So it is defined as follows: Shannon function of x is equal to minus x log x. So this is the first term. If we divide this by n, so we will have r over n log q r over n with a negative sign. So we exactly obtain this one if we plug here x r over n for x and then multiply by n. This term gives, if we switch here the numerator and denominator, we will obtain 1 minus r over n, that is 1 over n, which is 1 minus x if x is r over n. So we obtain here minus 1 minus x log q of 1 minus x. And the last term is a linear term. So when we divide this by n, we obtain r over n, that is x, times log q times q minus 1. So in general case, the Shannon function is defined using this expression. In the binary case, the last term here vanishes because q minus 1 becomes q1. But in general case, it has this linear term. And when q is large enough, then this linear term is actually very large. It's for q large, this is almost plus x. And so this is the most important term, and the Shannon function is very close to just the function, linear function x. So let's see on the using Wolfram alpha how the Shannon function looks in general case. So assume, say, that we want to plot the Shannon function for the three-letter alphabet. Then we just need to replace 2 by 3 here. And we will have then this expression. Oh, sorry, I forgot to add the linear term. Plus x times log base 3 over base 3 of 2. This changes the graph, of course. So we obtain the following graph, and when we are interested in the, say, Gilbert bound for the three-letter alphabet, so we need to plot 1 minus this function, and we see something wrong. Let's see. 1 minus, again minus. Let's do it correctly. Minus here, minus that. That's good. No, it's not good. Let's fix the brackets. Minus x log x minus 1 minus x logs minus x. What is that? Plus x log. So you see that it becomes 0. So the rate becomes 0 for when the relative distance is 2/3. So this is the sufficient condition, and let's plot it for a very large alphabet. For example, 256 symbols. So for such a large alphabet, it's almost a straight line from point 0, 1 to point 1, 0. So it reaches the x-axis very close to the point 0, and so it says that for all the parameters below this line there is a code. So actually we will prove now another bound, which is called the singleton bound, which is better than the singleton bound is necessary condition, which is very close to this sufficient condition for large alphabet. And for large alphabet, it's much stronger than the necessary condition we had before. So it's called again the singleton bound, and it states the following. So if an nkd code exists, then k plus d is at most n plus 1. So in other words, this means that k over n plus d over n is at most 1 plus 1 over n. So this is the same. This bound is means that for all the values of parameters below this straight line, the code is this. So for large alphabet, the sufficient conditions is very close to the necessary conditions. So we obtain the we have the exact knowledge for which parameter the code exists and for which there is no code. And a little bit further, we will describe those codes providing uh, on that line. So let's first prove this statement. It's based on a very simple principle which is called pigeonhole principle. In Russian it's called принцип ящика в деревле. По-английски это значит принцип голубей. Pigeonhole principle. It states that if m plus 1 pigeons occupy m holes, then at least one hole is occupied by at least two pigeons. And in our case, the pigeons will be the code words. So we will consider q to the m code words. And in each code word, so let's say this is a code word, and we consider first k minus 1 letters of that word, and there are q to the k minus 1 ways to choose those k minus 1 letters, and this will be our holes. And as the number of pigeons is q to the m and the number of holes is q to the k minus 1, by pigeonhole principle, we know that there is some k minus 1 prefix which is shared by q to the m I'm sorry. So the prefix should maybe I've chosen the length of the prefix in the wrong way. Let's see. There is a k minus 1 length. That's the mistake. The number of code words is not q to the m, it is q to the k, of course. So there is length k minus 1 prefix shared by at least q to the k over q to the k minus 1 code words. And this is q, and it is important that q is at least 2, so more than 1 code words. We call them, say, those code words q1, x1, xk, xq. So consider any two of them, say x1 and x2. They are certainly different, and so the distance between them is at least d. On the other hand, they have the same k minus 1 length prefix, so they can differ only in at most n minus k plus 1 letters. So the distance is at most n minus k plus 1, k minus 1, which is n plus 1 minus k. And so we obtain the third bound. D plus k is at most n plus 1. So the singleton bound is established. And now we will show that actually in the case when q is at least n and is a power prime, such code exists. So, and this will be, so to say, the perfect codes because they are on the bound, singleton bound, and so neither of their parameters can be improved. And they are called Reed-Solomon codes. So assume that Q is at least the block length and is equal to the power of a prime, say p to the m, where p is a prime number. For example, Q might be equal, say, to 29. So for any such n and m, there is a Solomon code. For any such n and q, there is a Solomon code whose parameters are n, the rate might be any, and the distance will be then will be as required by the singleton bound, that is n minus k plus 1. These are parameters of the code. And the code itself is the following one. So the messages have k symbols, and we will denote them by A0, A1, A Q minus n. And we will consider our alphabet as a field, since for any power of a prime there is a field, actually the unique field that has that many elements. We will assume that our alphabet is a field, f sub q, and the symbols will be considered as the elements of that field. So this is the message, and actually we will understand that message as a polynomial 0, 1 plus a1x no, sorry, here I made a mistake, not q minus 1 but k minus 1 plus etc. A q minus k minus 1 to the x k minus 1. So this is a univariate polynomial over that field. And the code will be based on the algebraic theorem stating that any non-zero degree k minus degree k polynomial can have at most k roots. That's why we need polynomial. So these are messages. And code words look like that. We fix some we fix some n elements in the field, pairwise distinct. And to this end, we need that Q is at least n, otherwise we can't choose that many pair distinct elements in the field. And we evaluate the given message or the given polynomial in all those points. And so we obtain n numbers from the field. And these are code words. So the code words are tables of the values of the degree k minus 1 polynomials in some fixed n pairwise different elements. So these are code words. More precisely, this is the code word which encodes the message P. So as promised, the length of the message is k, the block length is n, and the only thing we need to verify is that the distance, minimum distance, is at least n plus 1 minus k. So we need to prove actually the following lemma. If we have two different k degree k minus 1 polynomials, of degree at most k minus 1, then the number of i's for which I at most 10 for which they have different values is at least n plus 1 over k. Or stating differently, the number of y's which where they take the same value is at most k minus 1. But this is obvious because if p and q have the same value on some xi, then xi is the root of their difference. P minus q then vanishes in the point xi. And so the number of such points is at most the number of the roots of that polynomial, and that polynomial is non-zero because p and q are different polynomials. And so the number of xi is a root. and P minus Q is at most its degree at most k minus 1, so it has at most k minus 1 roots. So the number of i's where P and Q take different values is at least n minus k minus 1. So the lemma is proven. And so Ritz-Solomon codes lie on the singleton bound. That means that given n and q, we can't increase the rate keeping the minimum distance, or increase the minimum distance keeping the rate. They are perfect in a sense. Preparing to the next class, let's understand how we can decode Ritz-Solomon codes, not from errors, but just decode. That means assume that we have the code word, that is the value of the polynomial, how to reconstruct the polynomial itself. To this end, we have the so-called Lagrange polynomials, which allows to express the coefficient of the polynomial through its values. So actually, we do not need to have many points. It's enough to have k minus k points. So because the polynomial itself has k coefficients, and so it's enough to know its value in k points, and it is obtained as the sum of Lagrange polynomials of x times the values of the polynomial in those points, where the Lagrange polynomial L sub I is defined using the following formula. It's the product of x minus xj over xi minus xj where j ranges from 1 to k excluding xi. J is different from I. And this polynomial has the following feature. If we substitute xi for x, everything cancels and we obtain Li of xi is 1. And if we substitute any other xi, xj, we obtain 0 because xj minus xj is 0 for j different from I. So it has the following feature, and this implies that indeed our polynomial takes the value p over xi in the point xi, and it's not hard to see that there is a unique polynomial which takes certain values in k points. So this is one way to reconstruct the coefficients of the polynomial from its values. But to us, another way will be more important, which is the following way. To reconstruct the coefficients, we can solve the system of linear equations. Indeed, assume that the coefficients are a1, a0, a1, a1, and so on. Then each constraint that our polynomial takes certain value in certain points, say and x1 can be represented as a linear inequality in its coefficient, where the variables are its coefficient. Say, call the first value y1 and the last value, say yk. So each such constraint is expressed as a linear equation. Actually, x1 to the k minus 1, and here x k to the k minus 1 is equal to yk. So in these equations, the variables are a0, a k minus 1, and x1, xk, 1, 1, yk are some fixed elements. So these are indeed linear equations, and the determinant of that system of linear equation is non-zero. This is the well-known van der Monde determinant. And so the system has the unique equation, and to find that equation we can use, for example, the method of Gaussian elimination, and it's very fast. I mean, the method in linear time, it finds a solution. Here we assume that the field of operations are easy for us, so somehow our field is represented to us, so we can perform multiplication, division, addition, and subtraction efficiently. And this second way to recover the coefficients of polynomial from its values will be used when we will decode from errors.